The overall goal of the following experiment is to observe cardiac function and energetics in an isolated perfused mouse heart. This is achieved by perfusing a mouse heart in Lagendorf mode with Krebs-Hanselite buffer enriched with glucose and pyruvate. As a second step, a water-filled balloon is inserted into the left ventricle, or LV, which allows for the constant monitoring of cardiac function during the experiment. Next, the heart is placed into a 10 mm NMR tube and inserted into the magnet in order to assess cardiac energetics via observing the resonances of phosphocreatine, phosphates of ATP, and the inorganic phosphate. Results are obtained that show cardiac function and energetics based on the LV pressure waves and P31 NMR spectroscopy.
Hi, I'm Steve Kolwitz from the Mitochondria Metabolism Center in the Department of Anesthesiology at the University of Washington. Today I will show you a procedure for isolated heart perfusion combined with 31P NMR spectroscopy. We use this procedure in our laboratory to assess cardiac function and energetics in our bioengineered mouse models. So let's get started.
To begin this protocol, prepare 1 liter of Krebs-Hanselite or KH buffer. Introduce 5% carbon dioxide and 95% oxygen bubbles into the mixture for 10 to 15 minutes. Then, add 2 millimolar calcium chloride, followed by substrates 10 millimolar glucose and 0.5 millimolar pyruvate. For these experiments, 2 separate systems are utilized simultaneously. For acquisition of P31 spectra, a Bruker 14T magnet is interfaced with the Advanced 3 console and a computer equipped with TopSpin v2.1 software. For assessment of cardiac function, a custom-built heart perfusion system is interfaced with the PowerLab 430 data acquisition, equipped with the LabChart Pro 6 software for data analysis. The heart perfusion apparatus includes a MiniPulse 3 peristaltic pump controlled by an STH pump controller used to perfuse the KH buffer into the heart. Temperature regulation during the NMR experiment is critical. Heated circulators are used to maintain the temperature between 37.0 to 37.5 degrees Celsius while the heart is inside the magnet, and the temperature is monitored for the duration of the experiment using a fiber optic temperature probe. Throughout the experiment, the LV pressure and perfusion pressure are monitored via pressure transducers that are attached to a data acquisition system and displayed using the included software. A physiological transducer is used to monitor LV pressure, and a disposable blood pressure transducer is used to monitor perfusion pressure. Finally, an umbilical cord is used to supply the heated oxygenated buffer to the heart once inside the magnet. Prior to the start of the experiment, calibrate the pressure transducers with a standard sphygmomanometer. First, place no pressure into the transducer to zero the calibration. Then, inflate the sphygmomanometer to a high pressure. Enter this value into the computer program. Then, confirm that the pressure transducers have been adequately calibrated by inflating the sphygmomanometer to known pressures and verifying them on the computer screen. Once the pressure transducers have been calibrated, calibrate the NMR probe with a 10 mm NMR tube containing a standard sample of 150 millimolar sodium phosphate. Perform the calibration using the TopSpin software program. First, tune the sample to set the frequency of the phosphorus resonance. Then, shim the sample to create a homogeneous magnetic field. This initial calibration facilitates the signal and decreases the time necessary to begin the acquisition period once the heart is positioned within the probe. To start the mouse heart extraction, inject the mouse with 200 units of heparin intraperitoneally to reduce coagulation. After 5 minutes, administer 175 mg per kilogram of sodium pentobarbital intraperitoneally. Once the mouse is anesthetized, place it on its back and tape the arms and legs to expose the chest area. Perform a toe pinch to ensure that the mouse is fully anesthetized. Cut open the peritoneal cavity and chest with scissors and use forceps to peel back the rib cage and expose the thoracic cavity. With forceps, hold on to the lung tissue and gently lift the heart. With curved scissors, cut the great vessels behind the heart and continue slowly towards the head of the mouse until the heart is free. Immediately arrest the heart in ice-cold kH buffer. Keep the organs on ice and quickly remove the lungs. Identify the lobes of the thymus and gently peel them back to expose the aorta. Then, remove the thymus. Finally, isolate the aorta by carefully removing any surrounding tissue. Using microsuturing forceps, gently hold both walls of the aorta to expose the lumen. Then, carefully place the aorta onto the cannula made from 0.965 mm outer diameter polyethylene tubing. Hold the aorta in place with a microvessel clamp and quickly tie sutures around the aorta. Once the sutures are tied, remove the clamp. Use the forceps to carefully check that the cannula is above the aortic root. Add any additional ties that are necessary to hold the heart in place. Remove any extra tissue using the forceps and micro scissors. Then, make a small incision into the left auricle. Gently hold the heart and carefully insert 0.61 mm OD polyethylene tubing through the left atrium, left ventricular cavity, and out through the apex. Trim the excess tubing. Next, insert a deflated water-filled balloon through the atrium into the left ventricle. Hold the balloon in place using adhesive tape. Then, gradually increase the peristaltic pump speed to provide sufficient flow to the heart. Continue to perfuse the heart with kH buffer using a constant flow equivalent to approximately 2 ml per minute until the heart is placed into the NMR probe. Inflate the LV balloon with a small volume using a micrometer syringe to verify that the LV pressure transducer is functioning. For NMR spectroscopy, first carefully insert the heart into a 10 mm NMR tube. A wide bore spinner is placed around the NMR tube to help guide the tube into the proper position within the probe. Firmly attach the entire apparatus to the umbilical cord with adhesive tape. Next, slowly lower the umbilical cord into the upper bore of the magnet until the NMR tube containing the heart is inside the coil of the 10 mm NMR probe. Once the heart is in the proper position within the probe, adjust the peristaltic pump flow in order to achieve a perfusion pressure of 80 mm of mercury. Maintain the perfusion pressure by enabling the hold mechanism on the pump controller. Allow a 15 to 20 minute equilibration period for the heart. During the equilibrium period, adjust the volume of the LV balloon to achieve an end diastolic pressure of 8 to 10 mm of mercury. Then, optimize the spectrometer parameters in order to obtain the best possible phosphorus signal. Tune the NMR instrument by setting the radio pulse to the frequency at which the phosphorus nucleus resonates. Then, shim the sample to make the magnetic field homogeneous. After the equilibration period, begin multiple P31 NMR spectra acquisition. The acquisition period for each spectrum is dependent on the field strength of the magnet, the size of the sample, and the signal-to-noise ratio required for a specific experiment. Here, spectra are obtained using a 14 Tesla magnet by averaging the signal obtained from 256 radio frequency pulses of 20 microseconds with a 60-degree flip angle and delays of 2.0 seconds. This experiment will require approximately 10 minutes. A typical measure of cardiac function, the LV developed pressure, is obtained by subtracting the end diastolic pressure, or EDP, from the systolic pressure. In a normal C57 Black 6 mouse heart, LV developed pressure is typically between 100 to 110 mm of mercury at a fixed end diastolic pressure of 8 to 10 mm of mercury. Representative Starling curves are shown from control and aortic banded mice. Systolic function is represented by LV developed pressure over increasing LV volumes as determined by the volume of the LV balloon. Diastolic function is represented by EDP over increasing LV volumes. P31 NMR spectra of an isolated perfused mouse heart provide signals of phosphocreatine, or PCR, the 3 phosphates from ATP, and inorganic phosphate, or PI. Here, the PI peak is relatively small. This is typical of an aerobically perfused heart supplied with pyruvate or fatty acids in addition to glucose. During periods of ischemia, this peak increases while the PCR peak decreases.
I've just shown you how to prepare a mouse heart for perfusion so that both cardiac function and energetics can be measured simultaneously. During the experiment, it's important to make sure that the heart is adequately perfused. Otherwise, your NMR data will not be reliable. So that's it. Thank you, and good luck with your experiments.